So 20 years later, the science has caught up, if you like, with the fiction that was at the time produced in the book and in the movie. In hospitals, every day antimatter is used.
What is the next big discovery? Today we have Professor Carsten Welsch. He is a professor at Department of Physics in the University of Liverpool. He's an expert in antimatters. He has also worked at Large Hadron Collider. So a dream for all physics students. So thank you so much for taking your time out.
Sure.
So, first let's discuss the antimatter, because that's a very fascinating topic in general, because usually it is associated with a lot of science fiction. And even when I was young, when I was fascinated by new physics ideas, and I thought, oh, antimatter is it's like if matter comes to contact, boom, nothing, there's zero, there's nothingness. So what's antimatter, and what is in reality, what it is it?
Yeah, so I think you're absolutely right there, in that it's one of the things in science fiction that absolutely sparks imaginations, whether it's Star Trek or in Angels and Demons, Dan Brown's very successful book. The moment you mention antimatter, everybody seems to have an opinion about what it is. And at the same time, it's so fundamental to answering some of the very basic questions we have in physics, and where we have no answer to at all. So if we look at what physics tells us, fundamentally, at the beginning of time, so soon after the Big Bang itself, there should have been equal amounts of matter and antimatter. Yeah. And there should be similar amounts in the universe. And at some point, as you said, when they meet, matter and antimatter, they annihilate, they go off into pure light, and nothing should be left over. Yeah. That didn't happen, I guess, thankfully. Otherwise, we wouldn't be having that conversation now. Right. But the question is, and that's been puzzling scientists for a very long time, where has all the antimatter gone? We have no idea. So I guess in order to answer that question, we have to first look into how can we produce antimatter, how can we then do something with it, so how can we do measurements that tell us more about it, and can we maybe find a reason for why there isn't any antimatter, at least in this part of the universe. And it is a very recent research area, really, because if you think about it, when antimatter was first postulated through the Dirac equation, that was only about 100 years ago. So it was only at that time when people saw theoretically first, and initially they didn't actually believe it, they thought it was just a flaw in the equation, but they saw that there should be a mirror particle to the particles that we know. And a few years later, when they discovered the positron, they really saw that there is this parallel world where there is a particle which is exactly behaving like the particles we know, but it has opposite charge. Yeah. And you asked about how can we make antimatter, how can we examine it. So we need to really go back to the question of what builds matter in the first place, and ultimately these are atoms. So the first anti-atoms, and the most simple one, anti-hydrogen, was only produced in a laboratory in 1996. So I finished school in 94. That means when I did my final exams, nobody had seen an antimatter particle anywhere in this part of the universe. So it's really quite recent. Now it feels like we're talking about it all the time. It's still in Hollywood films, and it's routinely used really for all sorts of things. But it's quite a recent discovery ultimately.
Interesting. So what mysteries do we still have around antimatter in general, because like you said, we discovered positron, and nowadays we kind of understand the antimatter at least through equations. So do we have technological limitations to research more on an antimatter, or do we still lack a lot in theories as well?
Yeah, so I guess, so fundamentally, the big driving question is, why are we here? Why did we not annihilate a very long time ago? And why don't we see any annihilations in the night skies? Why are there not some antimatter galaxies that are colliding with matter galaxies and then they disappear? Why don't we see any of that? So what is the reason for that asymmetry in the universe? That is the question that drives us. Now, in order to answer that, what we are trying to do is have a very, very detailed look at the basic constituents of matter and antimatter and compare them and see, are there any differences? And we are doing this in many different forms. So if you take an atom, you have the nucleus and you have the electrons surrounding it, and between the electrons you have in some picture the shells, and the shells have some energy difference between them. You can measure that energy difference very, very precisely using lasers. You can do exactly the same kind of experiment also with antimatter, where the nucleus is composed of antimatter particles, and then instead of the electron, you have the positron orbiting around the nucleus. The energy levels that were found in experiments are exactly identical to the matter universe. In the next step, what you can also do is you can look into things like, how does antimatter behave in the gravitational field of the Earth? In fact, that's one of the things that we are trying to address in our AEgIS experiment. And you can take Newton's anti-apple and you can see, what does it do? Does it also fall down? Does it go up? Does it fall down differently? The problem is that these experiments, they are incredibly hard to do. There's one thing that we need in order to achieve our goal of directly measuring the gravitational impact on antimatter, and that is we need very cold positronium, because we need it as part of the production process. Now, positronium is an atom-like particle. It consists of an electron and a positron, so it's electrically neutral. It's not charged. It doesn't have a nucleus, so it's not really an atom, but it's kind of like an atom, and we can produce it. It lives very short, only 142 nanoseconds. But we have now managed, and very recently in 2023, to cool it for the first time. And this is just to give you an idea of time scale. So that process of laser cooling of positronium was described 35 years ago. And it's not like people haven't tried to do it, but it has been a very, very challenging journey. And only now, by using 3 different lasers and quite a complex apparatus, have we managed to do that. So I guess the message here is that these measurements, because they have to be so precise, they look at tiny differences between the matter and the antimatter world, that makes them so challenging. And I guess from a research perspective, also so interesting.
Interesting, very interesting. And I'm sorry, I'm just changing the topic, but like, you've worked at LHC, a dream for anyone who is thinking of taking physics as their career. So what was your experience there?
Yeah, completely different scale, of course. Antimatter experiments are typically maybe the size of a room at best, and the LHC really is the Lord of the Rings in terms of particle colliders. It doesn't get any bigger. Now, in my group, what we do is we develop a very sensitive instrumentation for precision experiments, like we just talked about, but also to characterize beams, like the beams in the LHC. So if you go to the very top energy, you are facing some new challenges in terms of how can you actually measure those beams. And the LHC recently or is about to receive an upgrade of its luminosity called the High Luminosity LHC project. And this will make the accelerator even more powerful to some extent. And it meant that some of the diagnostics, some of the monitors to characterize the beam would no longer work. Again, a perfect challenge for our group to then look into how can we design new monitors that can still measure the properties of the beams in the LHC with great precision. So you see, either at the very top energy end or in connection with antimatter particles, there are perfect challenges for somebody who is building particle accelerators.
Wow, that's brilliant. And like, because LHC has helped us understand a lot of fundamental particles, and one of the famous particle is Higgs boson. Like, it was famous with the name God particle. And what do you think, being in the domain of particle physics, what is the next big discovery?
Yeah. So predicting discoveries is kind of challenging because if I knew what would come next, then we would probably have done the measurement already. When you're asking me what is the big next challenge in particle physics, one of them is certainly to understand the Higgs boson in more detail. To me, this has been an absolutely amazing journey. I mean, imagine Peter Higgs and others predicting that particle such a long time ago and then requiring 40 years to build this ginormous machine, have all the world contribute to it, and then ultimately see in the experiment that actually it's true and the theory correctly predicts the Higgs particle. Absolutely mind-blowing, and I think a real illustration of how strong science can be. Now, understanding the Higgs in detail, we're still very far from that. And it's probably already clear that the LHC, even with its upgrades, cannot fully address this question so that we can really make sense of the Higgs. And for that, I guess we are pushing the energy frontier ever further. So we're looking at improving the quality of the beams in the LHC. And there are already groups also looking at potentially designing an even higher energy particle collider for the future. So there remain a number of very interesting challenges.
Interesting, because when I was doing my undergrad and we had this module of nuclear physics and particle physics, there one of the major discovery we were told of is of graviton, to understand to see if the fundamental particle for gravity exists or not, and learning from a person who already worked in LHC that LHC is still working to understand the particle they found 12 years before is a really interesting way to know that we it's theories need this is from my perspective, you can correct me if I'm wrong, that theories need mind and paper to predict, whereas technology needs billions of dollars and multiple countries to work together to just find one thing.
Well, I think I would look at it this way. What you need in order to achieve game-changing progress in science and innovation is, first, you need a good idea. So you need somebody who is not afraid of saying, where we are now isn't good enough, I have a different idea, and then to test that idea, because any theory is really ultimately only valid once you have tested it in an experiment and you have data that says, oh, actually we can't disprove it, so we can't fault that theory, and in the case of the Higgs boson we can actually show that this particle exists by detecting it in a very large machine, where, as you say, you are quite right, when you make these very big predictions you need a lot of people to work together in many countries, you need to combine resources, and you need to build something that the world has not seen before. And the LHC to me is a fantastic illustration of that power of international collaboration, because it's certainly an accelerator that no single country could have built, and now it is the absolute beacon in terms of fundamental research.
Yeah, interesting. And I've also learned about you that you focus on low energy antimatter, and in physics generally through movies we see that physics is mostly about high energy. We need more energy, we need high energy to throw the particles, high speed, everything is so big in numbers. So what makes this area of research of low energy more important and interesting?
Yeah, so actually we need both. We need the high energy and the low energy. For that to make sense, let me just take a brief moment to explain how we are cooking antimatter in our experiment, because we have to produce it somehow. I only need one equation for that, probably the most famous equation in physics, E equals mc squared. So if you bring enough energy into some area of space, you produce mass. That is what the equation says. And it doesn't say anything about what that mass is. It could be anything. It could be particles, it can be antiparticles. So what we do at CERN is we take a high energy proton beam and we fire it onto a block of metal, iridium. The reason for the metal and for iridium is it has a good thermal conductivity. It's solid, so it doesn't melt away easily. But fundamentally, what we are doing is we bring very much energy into that block of metal. So we're firing these proton beams onto the iridium block, and then with a very low probability of only 1 in a million, we produce antiprotons. So for every 1 million protons that are impacting on that metal block, we only get one single antiproton out of it. We can't increase the intensity of that proton beam infinitely, because at some point our metal block does start to melt. So typically we fire 10 to the 13 protons per shot, and then we get, for each million protons, one antiproton. So we only get 10 million antiprotons maximum per shot, which is every 2 minutes. So it's really difficult to produce these antiprotons in the first place, making it by far the most expensive material in the universe. I think 1 gram of antimatter is $1 trillion. It's an absolutely crazy number.
Yeah,
So, but then what happens is, so we fire that proton beam onto the block of metal, and then the antiprotons, they go everywhere at high energy. We have to catch them. We have to kind of bring them into some paths that we can manage, and then we have to decelerate them. Because for all the experiments that we talked about beforehand, measurement of the energy levels between the different shells, effects of gravity on antimatter particles, for any of these you need the antiparticles basically at rest. So what we do is, and that might sound strange for somebody who builds particle accelerators, we decelerate the particles. So we capture the antiprotons, and then we fire them into a ring, actually several rings, and we make them slower. We make them slow enough so that ultimately we can catch them in a particle trap. And the trap is basically a vacuum chamber where we have electric and magnetic fields, and we catch the antiprotons inside. We have a perfect vacuum, much better than outer space, so the antiprotons don't touch anything, because, as you said, the moment they touch anything, they disappear. So we have to have that perfect vacuum. We capture those antiparticles in the trap, and then we start doing our experiments. So you see, it's the entire process of ending up with antiparticles in a trap where you can really do these precision studies is incredibly hard. And I guess scientists like challenges, and that's why these kind of low energy precision studies are really what fascinates me and what drives me at the moment in my group.
Interesting. So, can this harnessing of antimatter be useful for more societal or general use, for like energy, medicine, or even for space travel? Do you think can we use antimatter in future in such domains?
So the first thing is, we are already using it for society all the time. In hospitals, every day antimatter is used. If you need a diagnosis by your doctor of your inner organs, very likely they will do a so-called PET scan. So a PET scan is a positron electron tomography scan. So it uses antimatter particles and particles to see what's going on in your body. What they are doing is they are injecting a radioactive isotope in your body. It decays, and because of E equals mc squared, it produces during the decay an electron and its antimatter mirror particle, the positron. So we are using antimatter for real-world societal applications already. Now the questions you are asking around energy production or space travel, it sounds amazing, doesn't it? Because the energy density in antimatter is just, it blows your mind. It's a factor of 1,000, 10,000 higher than any other fuel. So if you could produce, and that is a big could, because we can't, if we could produce antimatter in sizable quantities, it would be the absolute dream for so many applications. Now, unfortunately, our production rate is so small. Remember, only 1 million antiprotons, only one antiproton for each 1 million protons impacting on the target. So I think I saw a calculation at some point, and I think right now, if we took all the antiprotons that were ever produced in the history of mankind, so the last 40 years and we would annihilate them all at the same time, the energy release would not even be enough to heat a pot of coffee. So it's tiny amounts, and that is the big challenge in applications like energy production or space travel. So if we would find a catalyst, something that can increase that threshold, that cross-section of antiproton production, then it would indeed be a dream fuel, but that is for the future, that's not for now.
Interesting. Because this is my just hypothesis that great scientists and science fiction, or great directors of science fictions, they kind of give us a lot of goals to achieve in the future. It's because, like you just said, Higgs boson was in theory discovered 30-40 years ago, before we actually experimentally discovered Higgs boson. And I think, like what we talked about, graviton is like we know in theory for like another 30-40 years, or maybe longer than that, but it is still yet to be discovered through experiments. So I think these ideas and these theories, the ideas of science fiction and theories of scientists, I think they are more of a pioneer for what we as a society need to do in future.
It's also, I think it's an interesting and very stimulating dialogue between the artists, the creative directors that make films, and scientists. Because if you look back at the Angels and Demons book and movie, in the book, the plot is that they went to CERN, and there were some scientists that produce antimatter, and then there were some bad people that took a particle trap, took the antimatter, brought it somewhere in order to build a bomb, basically. At that time, nobody had envisaged to build a trap that could capture antimatter and then bring it somewhere else. It didn't exist. So it was really just, it was made up for the movie. They thought, in order to make our plot work, we have to take that antimatter and bring it somewhere where it's more relevant than having it in Geneva. So today, there is an experiment at CERN which has a trap that can capture antimatter to bring them to some other place. So 20 years later, the science has caught up, if you like, with the fiction that was at the time produced in the book and in the movie. So it's really, it's an interaction, and I think there's a lot to be learned from that. Art can inspire science, and science can inspire art, and ultimately the two areas really benefit from each other and should work together probably much more.
Yeah, that's really interesting. So how did you like this podcast? Do you have any question for me or any...
No, I think in general it's great that we can speak about our very latest research. I mean, this is really stuff that's happening right now. We have people taking data at CERN as we speak in our AEgIS experiment, and I think it's a fantastic way of bringing out our hands-on experience of dealing with such exotic particles, because they're not normally covered in mainstream media. So I think the podcast is a great way of making others aware of the interesting research that's going on here at Liverpool and places like CERN.
Interesting. Thank you so much.
You're very welcome.
Thank you so much for your time. Thank you.
Yeah, it is always really fascinating what's going on with antimatter particles.
It is, yeah.
I saw you there being all surprised when I said we're already using it.
Yeah.
Because that's, I mean, it's really something that